Today we will look at the evolution of the atomic model. At school you might learn about Dalton, Thompson, Bohr-Rutherford, and Chadwick. Today, that's information from the last 200 years. I'm going to take some time to look at the history from the last couple millennia so that you have to say, okay, there's more to this idea of the evolution of the model. So let's see, first of all, what we have. So first of all, you have to keep in mind, that's good, that first of all, this idea of the atomic model is the fact that we know nowadays that an atom is the basic unit of a chemical element. So let's see if I can show you an example. Here I have a rod of aluminum. If I take this rod, this one has a mass and a volume. But if I decide to cut it in half, and then I decide to cut it in half again, and in half again, and in half again, eventually I will get to a point where there's only one little piece of aluminum, one particle that I can no longer divide. It will be aluminum at its simplest form. So this idea of the evolution of the atomic model comes from this idea. How can we understand matter? So in order to do this, we have to go back in history. So going back in history, I was trying to see when were we thinking about matter the way we are today. So I went all the way back to Assyria, Canada, and that's about 500 to 800 before our common era. And here this was an Indian philosopher. So here he was thinking about his philosophy and his thinking, and he came up with the fact that our reality can be divided in four basic types. And the four basic types were air, water, fire, and earth. And you'll see that this comes through for a lot of centuries after this all around the world. So that's amazing. So let's see what else we have. So if you go back, so here we have in Greece before Socrates, like between, let's say, 400 years before our common era. And his thinking in philosophy was like this. All substance are made of eternally unchanging and indivisible. They are different sizes and shape. So I think if I remember well, I think the idea was if you take, for example, a shell, you go to the beach, you get a shell, and then you crush it, you will end up with little crumbs of a shell. But you still have a shell. So you can bring it down in small dust. It is still a particle of shell. But it will be different than if I take a rock and I break it down in small pieces into powder. This will be made of a different type of substance. If you have water, that's a liquid, you can have many drops of water. If you have a piece of gold, you break it down in small pieces, you would have a particle. So this idea of his, that we had, that matter was made of particles or substances that have different sizes and shape was interesting. And this is like, let's see, it's like 2023, 2400 years ago. Let's move on a little bit more in time. So here I have from ancient China. So here we have before our common era as well. And we have this idea that they are dividing, very similar to what they had in India 200 to 300 years from before, with fire, earth, water. And here they don't have air, but they have wood and metals. So here we have this idea of how can we find a way to describe our reality. A lot of it was philosophical. And second, we had to think about what is our reality. So here I put the indigenous medicine wheel, and you will notice that you have similar type of thinking. So here you have on the second entry, you have for north, air, for south, water, for east, fire, and west, earth. Then again, very similar to what was in China and in India several hundred years before. So it's interesting to see how the thinking is there, but we haven't been able to think, okay, scientifically speaking, how can we define matter? And here comes Dalton. So here we're in 1880 is the beginning of science the way we know it. And here is some of his ideas. So Dalton is more or less considered the father of what we know about elements. And I know that this is Eurocentric, but it still gives us a great idea. So his definition of matter goes like this. So first of all matter is made of small indivisible particles called atoms. So if you keep in mind, it goes in line with what was done before. All the atoms of an element are identical in properties such as size and mass, similar to what let's see, what's his name? Democritus had mentioned. Atoms of different elements have different properties, keeping in mind that if you have water, gold, or let's see, potash or carbon, they look different and they have different properties. And the atoms of different elements can combine in specific ways to form new substances. So let's see what he has here. So in his mind, you had matter was made of particles. So here, if I have aluminum, if you break it down in small pieces, at some point you end up with aluminum particles. If you have plastic in his mind, well, there was no plastic back then. Let's take a rock. If you take a piece of rock, volcanic rocks, if you break it down, you have particles of rock. If you take iron, particles of iron. If you have water, particles of water. So here, there were already some elements that were known at the time. So some example was oxygen. We knew that oxygen existed. It was important for in metallurgy, metallurgical advancement. Also, when there was fire. We knew about carbon when we have materials burning. We knew about iron, zinc, copper, silver, and gold from the blacksmith and the metalsmith industry over several centuries. We knew about mercury as a metal. So he was trying to say, okay, how can we divide what we know? And that was his idea, that atoms were made of small particles, as little beads or little marbles like this. Let's see if we can advance in our understanding of the atomic model from this point on. So here we have Thompson. So here we go from 1808. So that's about 100 years later. Then he came up with this idea so first of all, in the 1800s, another scientist realized that electricity was possible. The first electrical sources, the first like energy cells and the first batteries were created. So they knew about matter, and they also knew about electrons and static electricity, and they knew that charges could move. So here Thompson, in his work, he realized that if you have positive particles that that was created, so like an emitter of alpha particles, so they're protons, and they were going through magnetism or magnet, it would change direction. So his idea here is, okay, so we have magnetism that can affect matter. So somehow there ought to be charges in there, because at that time we were working with electricity, and we knew that from electricity in conductors, you could create magnets from having electrons moving in conductors. So in his idea, this is okay. We have Dalton that mentioned that matter was made of particles. Let's see if I can build on that. I will also keep his idea of particles, but because the matter is neutral, we're going to have the overall particle as a positive charge, and then we're going to have sprinkle in that particle negative charges. Just to remind you, scientists were playing with electricity and batteries. They knew that electrons existed and they were tiny particles. And that's the idea here of, in English, they called it plum pudding. I like this idea of raisin bread. So you have a bread and little raisins here and there. So we have our particles with a few electrons here and there. The particle is always neutral. That brings us to about, let's see, we go from 1904 to 1911. So we have Rutherford. So Rutherford is a scientist. He was in England for a while, then he was in Canada as well, went back to England. And his experiment was the following. So he also had something that created alpha particles. So here, positive particles. He realized that when you had those protons or those particles that were going through a foil of gold, in his mind, it was a solid. But then he realized that a lot of those particles would go through. So his idea was, okay, so we have particles like this, but somehow a lot of the particles will go through. So let's look at this part right here. We have the alpha particles, which are protons. They go through the gold foil, and they were mostly going straight. So that was with a small receptor right here. But what he realized is that there was something going on either side. So he expanded his screen to record his findings. And then he realized that when he extended his screen, he realized that there were some particles that were not following the main beam and they were a bit further. So he extended his screen and he realized there was some here. And he extended his screen to almost be a full circle. And then he realized that some of the particles coming from here, somehow, many of them, most of them would go straight, but some would change direction and some would even go back in the space. So here there was an issue with the Thompson model. If it was a full particle, nothing would go through. So now he knew that there was empty space that existed. But on top of that, most of the particles will go straight and some would change direction and some would go back. If you've played pool before or billiard, you'll know that when one ball goes to the other, you can change its direction. So his model had to change. So what he did, he used Dalton's and Thompson's particle theory. And he says that if you have a particle, most of the mass has to be inside. So in a small area, and he called it a nucleus. And that's how, when you have a particle that bounces on that dense circle or that dense nucleus, it would change direction or even go back. So that was Rutherford's contribution to the particle theory. So if you look here, we have our particle, our atoms, with most of the mass in the center. So that worked well. Everything is beautiful. Now, Rutherford was doing research and he had a student called Bohr. And Bohr, when he did his research, realized something as well that was interesting. He realized that his teacher, Rutherford, did a great job here. However, he realized that sometimes when you were giving energy to atoms, sometimes there was a delayed reaction and oops, energy would be given afterwards. So let's see if I can show you an example of what I want to show. So here's an example. So many of you have had, when they were young, they were small stickers. They were like light yellow in color. And when it was light, you could see it was light yellow. And when you turned it off, then you had this glowy green light that was coming. And interestingly enough, that light was not coming out forever. After 10, 20 minutes, then the light was no longer there. And in the morning, it was dark as if they did not exist. So somehow, this is matter. So here, this is this idea of phosphorescence. We have materials that are absorbing energy. And here in this example, there's a delay before the energy is given back. So if you think of this eagle, if the light is on, the energy from the light goes in the eagle. We turn the light off, and maybe if it takes 5, 10, 15 minutes for the energy to come out of the particles that makes this eagle. So the question here is, how does that work? So let's see if I can make a drawing for you. So we have here nucleus. So this was this idea of Rutherford. All the electrons are moving all around the nucleus. He realized that sometimes if you give energy to a particle here or a particle here, somehow there was a delayed reaction and then energy will be given and will come out of the atom. And he did not know how he could explain that. So he was thinking about the best way, and then he came up with the theory that we know right now. So let's see if we can figure that one out. 1, 2, 3, 4, 5, 6, 7, and 8 electrons. So he came up with this model that looks like a solar system. So 1, 2, 3, 4, 5, 6, 7, and 8. So here we have the same 8 electrons we had earlier. But here we have Rutherford that says we must have that looks like a planetary organization. So let's see if I can show that to you again. Perfect. So this idea that here electrons have their own place where they would be, and we could predict where they are at about 90% of the time. And this was amazing because if you look at my drawing here, his idea was if it happens that you give energy to this electron here will get more energy and it will go out to a different layer energy. So it has energy given to this electron. It will still interact with the nucleus here. And then we have electrons with energy. A little bit like if you have a little kid and you give it candies after Halloween. You get all excited for a little while, but it will not get excited forever. And then his energy or her energy will come down. And what will happen? This atom, when it will go back to its original spot right here, it had energy. So the energy had to go somewhere. And then you have energy that was given with a delay. And we have this energy. This energy could be in the form of light. If it was light, we have either a wavelength that we can measure that was quite fun to see. So here's an example. We have a particle that was given energy to go up the next energy level. And then when it came down, then there was some energy as form of wavelength or heat or different colors, UVs, that was just coming out. And this idea here of the model that is like a solar system came about. Now, interestingly enough, we call these Bohr-Rutherford diagrams because they both were from their research. So that was 1913. It's like 100 years ago, not that long ago. Then we had Chadwick, a couple decades after. He said, okay, we have Dalton that has particles, Thompson that has positive and negative particles. We have Bohr and Rutherford that has this idea of a solar of layers or energy level for the electrons. But what he realized is that when you had carbon with 6 positive charges, that creates the identity of an element, that sometimes the mass was different for different atoms. We call those isotopes. For oxygen, if you look here, we have 3 different atoms of oxygen, here with 8 protons positive. But if you look at the mass, it's 16, 17, and 18. The mass was different. All the same identity, but different mass. So in this idea, it says, okay, knowing about what we know about matter, we know that in the middle, we have a nucleus. The nucleus has positive charges, and most of the mass is inside the nucleus. So that means that if we have an element with the different atoms with different mass, so that means that in the nucleus, there ought to be something that creates mass, but not any charges. And he created what we call the neutron. Well, he did not create it. He brought forward the knowledge that neutrons existed. So what are neutrons? They are particles that are almost the same mass as protons in the nucleus, and they are neutral, so they don't change the charge of the atom. However, it changes its mass. But the model here is very similar to what we have for Bohr-Rutherford and even Thompson and Dalton. And that's why we see that in the last couple of 100 years, this is the recognized scientific model. We have particles, like Dalton said. We have positive and negative. like Thompson. We also have Rutherford that said that we have most of the mass in the center and electrons going around. Bohr added that the electrons had their own place to be. And then we have Chadwick that says in that nucleus, there's more than that meets the eyes here. And we have positive protons and neutrons that affect the identity of the atom and its mass. And I think that's the last one. There you go. So here's an example of, it's not exactly what I called a Bohr-Rutherford diagram, but let's see what we have. We have here an atom. In the atom, we have in the center the protons. And the protons is the identity of the atom. So here we have 4 protons. So if you look, let's see, in the past, I've mentioned that we have here Mendeleev. Oh, somehow I missed Mendeleev earlier. So we have 4 protons, which is the beryllium right here. We also have the positive charges in the middle. There's 4 of them. If there's 4 protons positive, there are 4 negative electrons all around. That works as well. We have the neutrons that are also in the nucleus with no charges. And we have the structure of what an atom looks like. So this is the basis of what we know of chemistry and how this can change in times to create the molecules that will be the topic of a next video coming up in the next couple of weeks. Now, as I mentioned about here, Rutherford, Thompson, I have forgotten about one person. So let's see if I can say about this one here. So if you're in science, you know about the periodic table. You know that they are organized to help us to know how many electrons are in each of the energy level. And if you have any questions on that, put them in the comments below. We also have the way they organize the families here, the group of atoms. Mendeleev is a Russian scientist at the end of the 1800s who said, okay, given the information I know, let's see if I can go to my French version here. I'm sure you can appreciate that. So here, Mendeleev in 1869 looked at the known matter that we knew. So he looked at this and said, is there a way for us to categorize and organize matter? So that's in 1869. So what he did, he took what we knew of the different atoms, he organized them with respect to how they react with other materials, how they react with themselves, and then he realized that some of these can be organized in columns and in rows like this. But the beauty of the Mendeleev's periodic table is that even though it is not exactly like our modern periodic table, what happens though is that he was the first one to look at patterns to see that if we have iron with an atomic mass of 56, we have nickel, cobalt here, 59, copper at 63, zinc at 65. He was the first one to recognize that given what we know about matter, there ought to be one that has an atomic mass of 68 and one that has an atomic mass of 70. So he was the first one to say, okay, I use science and what I know about matter to predict that some atoms, some matter, some new substances they have not been discovered yet. And I think that is the beauty for this one. So if we look here, there's some missing information with an atomic mass of 68 and 70. Let's look on the periodic table to see where that will be. So we have 68, so we had copper. Let's see again. So we had zinc and then arsenic at 75. So we had here zinc and arsenic here. We were missing 2 information. We're missing gallium. His prediction was the atomic mass of 68. And when we discovered it, we realized the atomic mass was 69.7 and the germanium at 72.6. These were unknown at the time. And if you look at his prediction, he was very close. So that's why we recognize him as an amazing scientific contributor to science and chemistry. So on this, these are the topics. This is the history of the evolution of the model, the atomic model. I think it's important to know. Often we focus on what's going on in Europe in the last couple of 100 years, but the knowledge has been going on for longer. On this, I'm going to put here a link to another video about chemistry, and I'll see you there.